Hello and welcome to this lecture on chemical process modeling and simulation. So with the derivation of conservation equations for overall mass, species as well as momentum and the constitutive relationships for a Newtonian fluid in basically one dimension as well as generalized to three dimensions, we have come to a certain stopping point, a concluding point for momentum transport or modeling of a flowing fluid. The next step to look at would be to see in a flowing fluid how is energy transported and how are specific species transported relative to each other. Both those would be the focus of the next set of lectures. For the first, especially with the fluid, the energy transporting fluids, there will have to be some background that will have to be provided on thermodynamics, and that would be the immediate focus of the next set of lectures. But before that, I would like to wrap up this part of this modeling of a flowing fluid by considering three problems involving momentum transport. All three are very interesting practical applications where we see such flows in practical engineering situations. And there are many such problems, much simpler problems and even more complex problems in Bird, Stewart and Lightfoot's classic textbook on transport phenomena. As a student, you are urged to solve as many of those problems as possible, and that will significantly strengthen your foundations in transport phenomena and modeling of fluids, which are momentum transport in a flowing fluid, right? So, however, I would like to focus on three specific problems for a given reason. None of these problems are so-called very straightforward one-directional momentum transport problems. They all have more than one direction involved. So I'm assuming that the simpler problems involving a single direction of momentum transport is something that you would study in your transport phenomena course, as well as probably in your fluid mechanics course, right? So I'm taking three specific examples where you will be forced to contend with more than one direction of transport in a practical situation, and try to see what kind of understanding we can gain in applying the conservation equations and the constitutive relations that we have derived so far. The first problem that I'm interested in presenting to you is one of an equilateral triangle duct, and I'm presenting this as an enhanced heat transfer geometry, though we are not going to do energy balances in this system just right now. So here is I'm going to start off this particular problem with a video that is embedded. It's an advertisement of a new heat exchanger that has been developed with equilateral triangle geometries.
Heatcraft Refrigeration Products is a leading global provider of commercial refrigeration systems and components. We offer specialized solutions for a variety of markets, including food service, supermarket, cold storage, and industrial and process cooling. The latest addition to our family of products is an air-cooled condenser featuring microchannel coils. This product is primarily intended for supermarket applications, but can also be used in various other applications, such as telecommunications and cold storage. Designed with sustainability in mind, this efficient condenser features a significantly smaller environmental footprint with outstanding operating cost and energy savings. This is primarily achieved through an innovative new microchannel coil design that provides over a 70% reduction in condenser refrigerant charge compared to traditional round tube plate fin condensers. The coil, composed of a series of flat tubes or channels, features a dramatically lower internal volume and a higher primary surface area than traditional round refrigerant tubes, allowing it to achieve comparable cooling capacity with much less refrigerant. For added energy savings, variable speed EC motors work with the microchannel coil to optimize efficiency, adjusting speed according to system demands and stabilizing head pressure. But energy savings aren't the only benefit these components offer. Combined, the efficient coil and EC motors reduce system sound intensity by 50%, 3.4 decibels lower than comparable air-cooled condensers with EC motors. Plus, our new air-cooled condenser features a 25% lower cabinet height, which significantly reduces visibility. What's more, this single metal coil composition offers unsurpassed corrosion resistance, providing improved reliability even in coastal environments. Finally, even with all these added benefits, this condenser remains within the same basic footprint as competing products, minimizing changes to store plans. And you can be sure our newest product is backed by the quality and dependability only one name can provide. Heatcraft Refrigeration Products, the name behind the brands you trust.
So here we see microchannel heat exchangers with triangular ducts for flow of the refrigerant. So this is the equilateral triangle duct geometry. You can see that two fluids flow, one flowing into the equilateral triangular duct and the other coming out of the duct. So basically these two are countercurrent flows in nature, and this could be used for your equilateral triangle heat exchanger design. And if these dimensions are small enough, then these are microchannel heat exchangers, which is what the advertisement that you just saw basically proposed. So since this is an equilateral triangle, the angle inside is 60 degrees, 60 degrees and 60 degrees, and side 60 is root 3 by 2, which is y by L, and cos 60 is a half, which is x by L, and therefore y is root 3 times x. Alright, and that's why this is root 3 times x and this is minus root 3 times x, because x is negative in this side. Now flow happens in the z direction. Velocity vz has to be a function of both x and y. Vx is 0, vy is 0. And this triangular geometry is given by the right hand side picture. So if you take your Navier-Stokes equation, then your x component velocity terms, all of these vanish. This is z component, right? Because you only have vz, right? And at steady state, this vanishes. Vx is 0, vy is 0. Vz is only a function of x and y, and therefore this term vanishes. So all the left hand side vanishes at steady state. Unsteady state, you will only have this term left. And then you have a pressure drop, and then your Vz is not a function of z, and therefore you have two terms here, and then you don't have your rho g. There is no gravitational force. So at steady state, Bird, Stewart, Lightfoot give the solution for this equation to be Vz is equal to P naught minus PL by 4 mu L H times y minus h times 3x square minus y square. So what you should do as part of this exercise is verify that this solution satisfies this Navier-Stokes equation that is given here. So this is one problem. The second problem is the problem of creeping flow into a slot. And this is a problem that we looked at when we considered molecular momentum, convective momentum flux tensor, right? So this is two-dimensional flow in Cartesian coordinates. Now, this is the problem. There is a slot that starts at x equal to 0 and with a thickness of 2b going in, and the fluid has to come in from a semi-infinite region, enter into the slot, and now flow through the slot, because this side and this side is all solid body, and therefore the fluid cannot flow past these walls that are present here. So therefore this is x equal to 0, y equal to 0, that is the origin point. Far into the slot, basically you have you have a parabolic velocity profile with both ends velocity being 0 because these two walls are stationary, and the maximum velocity being at the center. Now the fluid that is at x less than 0 has to creep into the slot, and so eventually in the slot Vx is a function of y, but before the fluid enters the slot, Vx and Vy are both functions of x and y. This is what happens when you have a large reservoir at x less than 0. So if you write your Navier-Stokes equation, then Vx is a function of x, Vx is a function of y. Similarly, Vy is a function of x and Vy is a function of y. At steady state, these two terms vanish. Vx and Vy are not functions of z, and Vz is 0. So these terms also vanish. There is no gravity effect that we neglect for the time being. So you have this expressions, these two equations basically, as the momentum conservation equations. But Stewart, Lightfoot again give the solution to be these. Vx is this and Vy is this. Verify that this solution satisfies the above Navier-Stokes equation, and also give an analysis of what happens to the pressure drop. Should there be a pressure drop, and if so, what would it be? What sort of assumption has been made in arriving at this solution regarding the pressure as a function of x and y? This is the second problem. The third problem is a very interesting problem of electrostatic dust precipitator. This is a practical device that is proposed in Stewart, Lightfoot again. So here is the problem. There are two plates, each of length L. They are parallel and are separated by a distance 2b. So at the entrance, the center of the entrance is the origin point, and this is the x-axis and this is the z-axis. So the top plate is at x equal to plus b and the bottom plate is at x equal to minus b. The pressure at the inlet is P0, the pressure at the outlet is PL. So there is a difference delta P over L that drives the flow along the Z direction or the Z direction. If you neglect the entrance and exit effects, you have a parabolic velocity distribution profile everywhere. And that parabolic velocity distribution profile is the same as flow between two parallel plates that you can that Stewart, Lightfoot has given a solution for. You can simplify the Navier-Stokes equation appropriately. Vz being a function of x, right? So that's what this velocity profile indicates. Vz is a function of x, right? And you can solve for it and obtain the parabolic velocity profile distribution. Now here is the question. Charged dust particles are also flowing along with whatever fluid that is flowing. Here it is said to be air. And the flow is laminar, clearly that's why you have a parabolic velocity profile. Now these charged dust particles in air have to be removed while flowing in laminar flow between two parallel plates. The two parallel plates are held or maintained under an electric field along the x direction. So this is E is equal to capital E into I indicating the unit vector along the x direction. This means one side of the plate, the bottom plate, should be positively charged, the top plate should be negatively charged, right? Because this field is along the positive x direction. Or if the top plate is to be positively charged, bottom plate is to be negatively charged, then this would be minus I. Either way, it's fine. What is the minimum length, L minimum, that is needed to collect or remove all the dust particles on either of the plates? Assuming the dust particles are either positively or negatively charged. So the positively charged dust particles that enter this region should get collected on the negatively charged plate. The negatively charged dust particle should get collected on the positively charged plate. Now what is this dark black line curve with various dots in between? This is basically the trajectory of a charged particle. This charged particle flows from one end of the entrance of the fluid to the other end at the exit of the fluid, and it gets collected at the bottom plate. So your Navier-Stokes equation, velocity of the fluid and the charged particles is Vz of x. So you can, all these terms vanish because Vx is 0, Vy is 0, Vz is not a function of z. At steady state, this is not, it's a 0. And then these two terms vanish. You can neglect gravity, and therefore you only have these two terms left, right? And so velocity of the charged particles in the x direction. Now why is there a velocity of the charged particles alone in the x direction and no fluid in the x direction? Well, there is, the fluid cannot go to either of the surfaces. They are rigid surfaces, the parallel plates, and therefore the convective bulk flow is only along the z direction. But there is an electric field that attracts or repels the charged particle, so it pushes the charged particles to one of the two plates, and therefore there has to be a velocity of the charged particles in the x direction, and that is given by u with a subscript x. Velocity of fluid in the x direction is 0. Now force acting along z direction that causes bulk momentum transport is minus delta p by L. Force acting along x direction causing molecular momentum transport is minus mu into Lw into dou Vz dou x or dVz dx, because Vz is only a function of x, dVz dx. Force acting along x direction causing transport of charged particles is minus E into capital E, which is m into dux by dt. This is your velocity, this is your acceleration, sorry. So ma is given by this electric force. What is the assumption, critical assumption, that is being made in writing all of these terms independent of each other is that charged particles are much smaller in size than the fluid particles. In other words, they do not alter the laminar flow of the fluid by their motion towards either charged plate across layers of fluid. So if you recall the trajectory that was sketched like this by Bird, Stewart, Lightfoot, if you were to follow the laser pointer, right? So what is happening? A charged particle, a dust particle that is here, is traveling across multiple layers laminae of fluid that is flowing when it goes from one end to the other end, right? So these charged particles, when they move across layers of fluid attracted by one of the charged plates, they do not alter the laminar flow of the fluid. Why is this? Because of course they carry momentum, isn't it? They do carry momentum in the x directions. Good. So they take the z momentum in one lamina and push it into another lamina, but this we are not considering this because the charged particles are much smaller in size, and therefore that momentum that is lost or transported by the charged particle in the x direction, okay, taking it from the bulk momentum transport, that is much smaller. And essentially, therefore, what this means by this assumption is that the z direction of the flow of the fluid and the x direction motion of the charged particles are uncoupled. They are not coupled. I can look at this analysis separately. I can look at that analysis separately. So if my charged particles therefore are much smaller in size than the fluid particles, then I can look at these two forces which are causing fluid flow, the transport of momentum of the momentum transport in fluids separately from the motion of the charged particles themselves. So this sort of simplifies our system. So this equation, the Navier-Stokes equation, gives the velocity profile for the fluid and charged particles in the z direction. I will use the same velocity profile for the fluid along the z direction as well as the charged particles along the z direction. But I will say that there is no fluid velocity in the x direction. There is a charged particle velocity in the x direction that is entirely caused by this and the electric field, and these two are uncoupled with each other. So how do you go about solving this? So this is your velocity profile for the fluid and charged particles in the z direction. You can obtain this. This is the first step to the solution. Then I can integrate my f is equal to ma equation, which is minus ee is equal to m into dux by dt. I can integrate that and I can get the velocity of the charged particles in the x direction. Displacement of the charged particles in the x direction is x of t. This is dx by dt, and I integrate this. All right. So what is the maximum time that is taken for a charged particle to get collected at either plate? So suppose the top of this box is one plate and the bottom of this box is the other plate. So this width is 2b, isn't it? Now the time taken for the maximum time taken for a charged particle to get collected at a plate is basically the time taken for a particle that is entering at the top of the region, the flow region, which is x equal to b, and it has to reach all the way to x equal to minus b just as the fluid it is present in the fluid particle, it is present in exits the region between the two parallel plates. Okay, so this is the maximum time taken. Suppose a particle were present here, it would probably get collected at a faster time. If a particle were present here, then this would probably get collected at an even faster time. But the particle that is charged particle that is present at the other plate surface, it gets repelled by that plate and attracted by this plate. It has to travel the entire x distance, maximum x distance of 2b. All right. So if I substitute this to be 2b, all right, then what will be the time taken for that? That is my t max. By this time, this is my velocity along the z direction. This is dz by dt. The fluid would have moved, displaced by a certain distance. So as the charged particle goes from here to here, from plus b to minus b, the fluid that it is present in would have gotten displaced along the z direction. How much is that displacement? That displacement is the minimum length that I need because if I give that much length, then my particle would get collected here. If, for example, the fluid were stationary, I only had basically the electric field, then the particle that is charged particle that is here would directly go down and get collected here. But since the fluid is flowing, the particle as it is coming towards the other plate in the x direction, it is also being displaced along with whatever fluid particle it is present, and it has to get collected here. So that is the length that the fluid particle would travel along the z direction in this time, and that is an integration of this. This is dz by dt, so I integrate this and integrate for z of t, substitute t equal to t max, the corresponding length is L min, and this is the solution that you are asked to obtain. So this is the final answer. You can verify that you are able to get this answer indeed. Okay, so this is the minimum length needed to collect all the charged particles that enter the region between the two parallel plates, provided that the flow is laminar and provided that the charged particles are much smaller than the fluid particles, to the point that their movement under the influence of the electric field can be decoupled from their movement along with the fluid particles that they are associated with. All right, so this is basically, by this way we have designed for the capacity or the length of an electrostatic dust precipitator. Its unit variable would be the length of the plates, and of course the distance between the two plates, 2b. So if you fix a 2b, you need a certain length, right? And this is a process variable, the pressure drop of operation and the electric field that you apply. The larger the electric field that you apply, the shorter the length that you need. The larger the pressure drop, faster the flow along the z direction, therefore you need longer length to collect it, right? And then larger the distance between the two parallel plates, of course the longer the time taken for the charged particle to come to the other charged plate from the top charged plate, and therefore longer the length that you would need. So more the retardation of the fluid flow by shear, the lesser that the fluid would get displaced along the z direction, and therefore you are shorter the L that you need, and so on and so forth. So basically this gives the relationship between the various process and unit variables and the design variable, which is your length of the two parallel plates that you need. So with this we come the end of this lecture, and so this basically is an assignment for all of you to try and work out 3 problems, all 3 involving either flow in multiple directions or at least velocity being a function of more than one direction. And so they are all slightly more complex problems, more challenging problems than what you would encounter in your basic fluid mechanics or your basic transport course. And this all of these apply the momentum conservation equation that you have learned in these lectures. So if there are any questions, as always, I'd be very happy to answer those questions. You may post them at the YouTube channel, or you may write to me or contact me. Otherwise, I'd be very happy to answer your questions. Good luck trying to solve these problems. Thank you for listening to this lecture. I hope you all have a wonderful day. Thank you.